Today we will continue discussing our two-machine infinite bus system. Last class, we obtained finally a code that can determine the equilibrium point of the system. And we even invoke the solver to solve the initial value problem from the equilibrium point. As we didn't have any disturbance, all the variables, state variables and algebraic variables, remain constant over the simulation time. The equilibrium point, as we have discussed so far, will be determined by setting the derivative of the state variables to 0, and we find the values of xe and ye that will satisfy this condition. So we obtain in that fashion the equilibrium point. But now we're going to assume there is a disturbance. What disturbance? We have considered in the past short circuit, and we will continue using short circuit for this system. Short circuit is a type of disturbance that do not create any power imbalance. So that is very attractive for the model that we have, because we do not have a governor in a turbine model. If there is a power imbalance in the system, then the power generated from the generators need to be adjusted. And that will not happen with the model that we have so far, as we have not described yet the governor in turbines. So we will stick with the short circuit for now. At time t0, we have a short circuit, but there is a distinction in what will occur with our variables. On one side, we have the state variable. And as we have discussed so far, state variables are going to be related with some energy stored in some component. Energy, as we know, cannot have discrete changes over time. So at time t0, the energy stored in a component cannot have a step change. Therefore, the conclusion of this is that the state variables cannot have a step change. So if at time t0 we have a disturbance, the state variables will remain constant. And that's the condition that I have right here. On the other hand, algebraic variables have been derived with the assumption that they do not involve any energy store energy whatsoever. Therefore, they are allowed to have discrete changes. So that's the problem we need to deal now when we have a disturbance. We need to find a procedure that can help us to obtain the new algebraic variables when a disturbance occurs at the system. So at time t0, what we will have is that situation. Now, because y is not going to be at the equilibrium point, then the derivative of the state variable, some of them will be different than 0. And therefore, the state variables will start drifting away from the equilibrium point. When we have a disturbance, now a short circuit in this case, that will create a fundamentally important change in the grid. We're considering three-phase short circuit. And for this problem, we're considering that the short circuit occur at bus 2. So the voltage at bus 2 all of a sudden is sent to 0. So to consider that in our grid representation, then the algebraic equation that we have need to be modified to consider that current condition for a short circuit at bus 2. So what do we have to do? First thing, we need to find this new algebraic equation when we have the disturbance, short circuit at time t0. Then, using the algebraic equation as xe remain constant, and as we know the new algebraic equation, we need to find y is c, the algebraic variables, right at the moment of the short circuit. And when we calculate this value, we will use this as an initial point to solve the initial value problem. And we will simulate the system for some time during the short circuit at bus 2. So that's the steps that we need to take. In general, solving the set of algebraic equations, because they are nonlinear, can be solved with an advanced technique like Newton-Raphson. So if we have an initial guess for what could be the solution, then we can iterate, calculate the Jacobian of these nonlinear equations, and iteratively we can find a solution with some error under a tolerance. So that one would be one way, but because we don't want to spend much time on this, we're going to consider some assumptions that will help us to simplify the problem. What assumption one? We have the model for the synchronous generators. So given the terminal voltage, we need to determine the new condition for the current in the system. But as you can see here, the current will depend on this internal voltage, but this internal voltage depend on the current. So that coupling will add some extra complexity that we want to simplify. So with the assumption that xq prime is equal to xd prime, this dependency on the current is eliminated. So as the state variables remain fixed at time t0, the state variables will be given because they remain constant at that moment. And with that voltage known, and also with the terminal voltage known, then we should be able to determine what will be the current IV and IQ for a particular synchronous generator. The assumption two, we're going to assume that all loads are modeled as constant impedance. So the assumption we're going to make is that the given power we have for the load, power, consumed power, is going to be the power absorbed at nominal condition. So if the voltage at the terminal of this load is 1 per unit, is nominal, then the power absorbed by that load is going to be the specified power. So with that in mind, we can have the expression of the complex power in terms of the voltage magnitude square over the conjugate of the impedance of the load. As we're assuming these are nominal condition, the terminal voltage is 1 per unit, and therefore we can solve for the impedance CL. So by solving for CL, finally, we obtain this expression for the impedance. That's the impedance determined assuming nominal condition. But as the impedance is constant, that's the value that will keep for any terminal voltage at that load. So in our system, we're going to assume that this time t0, when we have the disturbance, is actually 0. At time 0, we will have a short circuit at bus 2. So the system representation is what we have here in the circuit. As you can see here, the voltage B2 is sent to 0 because we have a short circuit. Because of that short circuit, you see there is no coupling of that synchronous generator with the rest of the system. So that the representation for the synchronous generator 2 is going to be simply that equivalent circuit. So as the internal voltage for the machine E2 is given, because the state variables cannot change instantaneously, this quantity will remain constant at 0 minus. It will be the same state variable at time 0 when we have the short circuit, then E2 will be given. As the voltage B2 is 0 because we have a short circuit, then we should determine the current I2. By definition, the current I2 is right here. We know again how much is the angle delta 2. So from this equation, we should solve for IQ2 and ID2. For the rest of the system, then the second part of the system, because we have a short circuit, is what we have right here. We are isolating the generator 2 from the rest of the system. So the second part of the system is what you have right here. This is the impedance between bus 2 and 4. And because the voltage at bus 2 has been sent to 0 due to the short circuit, we have that representation. What we need to do in this system, we need to determine initially what is the voltage in magnitude and angle for buses 3 and 4. The voltage at bus 2 is already determined. It's a short circuit. Magnitude of B2 and angle of that voltage are going to be 0. So we need to determine first voltage B3 and B4. All the algebraic variables we need to determine. The two currents for the synchronous generator 2 that I explained already how we can determine. We need to determine the currents at synchronous generator 3 and the voltage magnitude and angle at buses 3 and 4. Explicitly, here is the solution for the current at synchronous generator 2. So we have, because of the short circuit, all this internal voltage will fall in that impedance. So we have this equation right here. We can cancel this exponential term, and then we can do the multiplication on that part, and we have a real term and an imaginary term. By having the equality that the real term on the left side is equal to the real term on the right side, then we can solve for IV2 and we have an expression. So all we have to do is to take EQ2 prime and divide that by XD2 prime. By doing the same with the imaginary term, if the imaginary term on the left is equal to the imaginary term on the right, then we can have an expression for IQ2. For the rest of the system, then, we have an equivalent representation. And here, because we want to simplify this, we're going to remember from circuit analysis that if you have a voltage source in series with an impedance, that is going to be equivalent of having a current source in parallel with that impedance, where the current is obtained as the voltage of the voltage source divided by the impedance. So we will apply this equivalency. And we need to find where do we have a voltage source in series with an impedance. And we have two places. One is going to be there, the voltage and the infinite bus in series with the impedance from bus 1 to 3, and the internal voltage in synchronous generator 3 and the impedance of the synchronous generator 3. So we will express those two branches using the current source equivalent. By doing that, now we have this for the infinite bus in series with impedance C13, and we have this for the equivalent representation of the synchronous generator 3. And we can reduce this further because the impedance here with this one are in parallel. We can define that as the equivalent impedance 2. And this impedance C24 and CL are in parallel. We can define that as the equivalent impedance 1. And then we have this reduced representation. These two current sources here and here, because they are injecting current to bus 3, we can add them and have just one current source with a total current injected given by this term. As you can see here, these depend on these impedances, the voltage at the infinite bus and the voltage E3, which is completely given because the state variables do not change from time 0 minus to time 0 when we have the short circuit. Finally, by using simple circuit analysis in this circuit, we can obtain voltage V3. And to do that, we can obtain equivalent impedance there. And we are going to call that equivalent impedance 3, which is the parallel of the equivalent impedance 2 in parallel with C equivalent 1 plus Z34. Finally, that's the resulting circuit, and voltage V3 is nothing else than the product of the equivalent impedance multiplied by the total current of that current source. So we obtain voltage V3. By looking at this circuit that we have above, if you know the voltage at bus 3, by voltage division, then we can obtain easily the voltage V4. And that is the expression that I have right here. So with these simple steps, we had been able to obtain the voltage at buses 3 and 4. With those voltage at buses 3 and 4, we can also obtain what I discussed before. We did it here for the machine 2. We can calculate the currents IV and IQ for machine 2. But the current for machine 3 can be determined easily also using the circuit. So here, let's look at this part of the circuit. We know voltage V3 now. We have determined all bus voltages. We know the internal voltage E3. We know this impedance. And by Kirchhoff voltage law, we can have an equation we can use to determine the current I3. If we know current I3, then we can determine the components, IV and IQ of this generator. At the end of this procedure, then, all algebraic variables has been determined. Then we can solve the initial value problem in a specific window of time from 0 to the clearing time. And we're going to start from the state variables that have remained constant at time 0 and the new algebraic variables we have determined because of the short circuit. From this point, we integrate the set of differential algebraic equation and we have a solution over this window of time. We need to remember, because we have a short circuit, algebraic equations have been modified. Therefore, the function that we use to specify all the set of differential algebraic equations need to be modified and updated to the short circuit at bus 2. At the clearing time, we're going to clear the fall. So the grid will be subject once again to a sudden change, and the voltage at bus B2 that was sent to 0, all of the sudden is not 0 anymore, and the system will be modified once again. We apply the same procedure. The state variable cannot change instantaneously. So the state variables at this clearing time, when we don't have the short circuit anymore, will be exactly equal to the value that they have at the very last moment when we have the short circuit. So we need to consider that condition for the state variables. For the algebraic variables, once again, they will have a discrete change. And we need to determine, again, what is going to be the new values for the algebraic variables considering the new condition. What is the new condition? Voltage B2 is not 0 anymore because the fault has been cleared. As you can see again, we have a system that is not decoupled anymore. Generator is not decoupled from the rest of the system, and they all interact together. A simple step we can do here, we can obtain again an equivalent representation for these two voltage sources using current sources. If we do this, then the representation of the system is this one. The value of these current sources is going to be given because the voltage E2, voltage E3 are going to be given. We know what are the values of the state variables. So as you can see in the circuit, with two current sources and one voltage source that exactly define the voltage at bus 1, we can apply nodal analysis to determine all these voltages. So what we're going to do, we have the full expression for the matrix expression for the model analysis. We have the current injected at each bus 1, 2, 3, and 4. As we have considered that the load is represented as a constant impedance, we are going to add this constant, the admittance of this load. We're going to add it to the modified Y bus of the system. The same thing we will do with the impedances from generator 2 and 3. We need to add this to the modified Y bus of the system. When we do this for the load, we need to consider something else. Now, by adding this impedance into the Y bus, we're already considering in that fashion the incidence of this load in the system. So therefore, we don't have to specify any injected current in that bus because that is already considered. That's why the current injected at bus 4 in this representation is going to be 0. As we know the voltage at bus 1, we don't know how much is the current injected at bus 1 yet, but we know the voltage at bus 1. We can split this matrix representation, and we can have this partition for the vectors of voltages, vector of currents, and the Y-bus modifier of the system. Y1 is going to be a scalar because it will relate the injected current I1 with V1. Y2 is going to be a row vector with 3 components because once again, it will relate the injected current in bus 1 with 3 voltages, V2, V3, V4. Y3 is going to be a column vector because it will relate voltage V1 with the injection at buses 2, 3, and 4. Finally, Y4 is going to be a 3 by 3 matrix because it will relate the injected current with the voltages at buses 2, 3, and 4. As we already know V1, we can use the second block equation from here, and we can have this description. V1 is the voltage at the infinite bus, so this is given. We know the current injected at the buses 2, 3, and 4, and therefore, by using this equation, we can solve for the voltages V2, V3, and V4. And here's the equation. And at the end of these steps, we are able to find the 3 voltages at the system, V3, V2, V3, and V4 phase in magnitude and angle. So these 6 algebraic variables has been determined. With these voltages determined, then we use the model of each synchronous generator to determine the components Q and D of the current. Differently from the case before, when we did have the short circuit, this voltage is not 0 anymore, so we have to include that voltage there to determine the component D and Q of the current in the machine. For the synchronous generator 3, the equation is no different as the equation we used before, because V3 was different from 0, and once again here, voltage V3 will be different from 0. So by solving this equation, we can determine the D and Q component of the current at generator 3. At the end of these steps, then we will be able to determine all algebraic variables, and then we can solve the initial value problem in a window of time from the clearing time to a final time for simulation. It can be 10 seconds, 30 seconds, whatever we pick. And the initial point will be for the state variables, it will be the same values we have at the last moment before we clear the fault. And for the algebraic variables will be these new values we have determined. Note that as the fault has been clear, the algebraic equation must be restored to those that we had before the short circuit. I have already included all these calculations in our code, and this code has been uploaded to Canvas. So we will run some simulations right now. We will have some modification in our code from last class. Now the impedance from the load at bus 4 will remain fixed, not the power, but the impedance. So we calculate that impedance, and I am creating this, defining CL as a global variable. So we have access of CL from any point in our code. What other modification we have to do? The solution of the power flow, when we solved before the fault, what was the equilibrium point? Why? Because the power flow now need to be done, assuming that the consumption at bus 4 is through a constant impedance, not constant power load. So that needs to be modified. What is the procedure to modify the equations? Think about it. I made all the changes here. We have the same initialization we have last time. Exactly the same. And here, I made some changes based on what we have discussed. The first part, I'm going to simulate from -1 to 0, just to have a reference, because the system is in a steady state. And at time 0, we will have the short circuit. So we will simulate here, and then at time 0, we will have the short circuit. What do we need to do? Initialization of the algebraic variable. The state variables remain the same, but we need to calculate algebraic variable using the procedure we have discussed in the whiteboard. I created a function for this, so the function will follow the same step that we discussed here. With that initial condition, we will simulate from 0 to the clearing time, let's say 100 milliseconds. And we will invoke the solver using a set of functions now that are called h at the short circuit. What is the difference with the previous function? We have a short circuit. Where is the difference? Of the grid, right? The equation that we have for the grid, we have 6 equations for the grid. Now, 2 of them are different. Why? Because we have a short circuit at bus 2. So B2 and theta 2 need to be 0. So we need to modify that. And also the other equation, remaining equation, need to consider now that B2 is 0. So we need to modify that representation. We solve it. At the clearing time, we will get the last set of values, because with that, we need to keep fixed the state variable at that time, 0.1. But because we're modifying the grid now, there is no short circuit, we need to calculate the algebraic variables. They will have sudden changes. So we will have a procedure here I call fault clear initialization. What is the procedure? This one. Similar equation, but now the short circuit here is removed. You can check the function for that case. And from here, we will simulate from the clearing time to 30 seconds, for example. We will pick the solution before the fault, during the fault, and after the fault, and we will put them all together in line 131 and 32. And then we will plot, okay? So that's the system. We will simulate this. Let's say this is 0.1, and this is the solution. And now the system is getting more complex. Why? Because how many state variables do we have? 4. Can we plot this completely in the phase plane? No. So we need to look at the phase plane just from one angle. Here's one angle. We look at just delta 2 and omega 2. That's the behavior. Very like a regular pattern, right? So what we saw here for the single machine system. And this is another way to look at this, which is the difference between omega 2 and omega 3 and delta 2 and delta 3. This is a little bit not regular off. That is looking also at the phase plane from a different angle as well. Yeah. And this is the solution for delta and omega. What do you see here, for example, the speed? And let me make a zoom. Anything surprising?
The second hump is higher than the first.
Yeah.
On the red.
Generator 2. Why do you expect that it will be larger?
There's a bigger imbalance after when the voltage at bus 2 is 0. It's gonna, the electrical power is gonna be 0, so this machine's gonna accelerate more.
Yeah. How is the electrical power in machine 3 during the short circuit?
it had to increase because of the short circuit?
Probably not. The voltage is reduced, but the voltage is not zero. So you are still generating electrical power. So the mechanical power minus electrical power will not be maximum PM, but it will be somehow reduced because you still have electrical power. Then the acceleration in machine 3 is not that large, right? Because the fall happened in bus 2. What happened if the fall happened in bus 3? We might have something different, right? What else do you see in the plot? Blue and red line speed for machine 2 and 3. They are almost in phase. That's not something that we should expect when I say that we will see more interesting dynamics. What is the meaning of the two being in phase?
They're not oscillating against each other. They're not exchanging energy.
They're not exchanging energy, yeah. When the speed increased for both of them, what is happening? They're getting kinetic energy. They're receiving energy from somewhere. Where? The infinite path. When the speed for both of them is going down, what happened? Both of them at the same time are sending energy to the grid, right? To the infinite path. So the exchange of energy in this case is as its generator 2 and 3 work together and oscillate with the infinite bus. Why is that? We have a short circuit at bus 2. How much is the inertia here? 3 seconds. How much is the inertia here? 6 seconds. Or backward. Let's check. Let's check. We have, I think this is backward. We're going to make this change to discuss, and then we will leave it until here. Generator 2, 6 seconds. Short circuit at bus 2, generator 2 has 6 seconds of inertia. How much is generator 3? 3 seconds. What happened? We said that the short circuit at the terminal will send the power to 0, electrical power. So it's going to accelerate a lot. But how much is the inertia? 6 seconds. It's much larger. What about if the inertia of this guy is smaller? It will deviate even more. So it seems that this disturbance is making the two machines oscillate together. So we will trick it. What about if generator 2 has 3 seconds and this 6 seconds? What do we expect? Machine 2 should deviate even more. Yeah, is something different now, or is about the same? Well, it's always hard to see when you have 4 dimensions, but it seems that these plots in the phase plane are different now. They're not kind of the conventional one, right? So something is different, but we take a look at the speed. What do you see now? Something strange going on. Now the dynamic is different than before. Are generator 2 and 3 oscillating together with the infinite bus? No, now they're not. It's not clear. And maybe at the end here, maybe they are, but the exchange is not. No, they're counterphase. So basically, what do we have here, David? We're very different to what we had before.
Here's, I guess,
Let's
we call it an inter area. You can maybe look at the period. And
yeah, we don't know if we have areas here or not, but we can say this. There is exchange of energy between generator 2 and 3. Before, the exchange of energy was between 2 and 3 together with the infinite bus. Now, clearly, there is an exchange of oscillation, the energy between 2 and 3. So the behavior is different. How much is the energy that involves 2 and 3 with the infinite bus? Is it going to be larger than the energy between 2 and 3? Just by intuition, what would you say? and we need to double check. And I haven't looked at the numbers in the plot yet, but what do you expect if you have two machines, one with 3 seconds of inertia and the other 6 seconds of inertia, and they're oscillating against each other? Or you have two machines together, one with 3, one with 6, that which give a total of 9 seconds oscillating with the infinite bus. Which oscillation might have more energy?
The one with the infinite bus mirror exchange.
With the two together, So that's something we can check here. But clearly in this simulation, we observe now the system will respond differently depending on what fault do we have. Where are the faults occurring? What is the inertia you have in that area? And of course, the topology and many other things. Okay, guys, so I'm going to leave this here. I want you to take this code and play and find the critical clearing time. How we're going to do it? We apply it in the same way than before. We're going to create a vector with different clearing time. We will invoke this solver in a loop. We will simulate all the solution. When we determine instability, we're going to start like narrowing down the critical clearing time until we find the right time. And we can do that for two cases. When the inertia of machine 2 is 6 and this 3 is 3 seconds, and when the values are all the way around, this is 3 and 6, and then 6 and 3. And we will see, will that have an impact on the critical clearing time? Yes, it will. It will. Any question? We're almost done with this. I will make a summary next class about this, or maybe have some additional simulation to discuss, but this is almost done with this part. And there is a homework that is going to be related to this system. Yeah. Thank you, guys.